second talk is Dr. Yijiang. The speaker is Dr. Yijiang from ETH. He's also my colleague from ETH. He is now a postdoc researcher in the Department of Computer Science at ETH. He researches at the intersection between architecture, computing, and robotics to make design and construction more connected. Yijiang got his PhD in the Building Technology program at MIT's Department of Architecture. Before MIT, he studied applied math and did research in computer graphics at the University of Science and Technology of China, where he researched his Bachelor of Science. And today's talk is about algorithmic planning for robotic assembly of building structures. So Yijiang, the floor is yours. Please go ahead.
All right. Can you hear me okay?
Yeah, maybe share a screen. I can check again.
Yep. Share screen. Can you see the slides okay?
Yeah, it's perfect.
All right. Yep. Thank you very much, Ziki, for your very warm introduction. It's always nice to be introduced by your friends and colleagues. And thank you very much for the invitation. I'm very thrilled to be here today to share my work with the Asiagraphics community and to hear from you and to share this idea that I would like to promote to use computation to bring architectural design and construction closer together. I have a bit of an unusual background, so I quickly go through my kind of personal story. I was trained in applied math back in my college days in University in Science and Technology of China. And then through researching computer graphics, especially in digital fabrication, I got very excited about the use of those mathematical tools to contribute to architecture, to the built environment. Then I moved to MIT and I did my PhD in the building technology program there in the Department of Architecture, where I learned about how design, like structural and architectural design, can be driven by structural performance principles. And for my research, I focus on performance in terms of construction, especially to make robotic fabrication more flexible to design inputs. And now I'm a postdoc fellow at the Computational Robotics Lab at ETH Zurich, where as a lab, our research unites under the theme of advancing robotic intelligence. And for my own research, I focus on building collaborative autonomy among multiple robot agents to boost construction efficiency. So in general, I kind of identify myself as a half computer scientist, half architecture engineer, and I've worked on algorithms to generate structurally efficient forms, design with reused building materials, and innovate new robotic fabrication processes and applying automated planning methods to program them to build structures more effectively. And a common theme that cut across all of these projects is that I would like to use computation as a medium to study the relationship between design, object, the builder, the agent who built the design, and the final outcome, the physical construction. And under this theme, one exciting topic is to study how we can advance robots' intelligence and ability to build things. In my vision of a future building industry, we can just give the drawing of a building design to a team of robots, and they will try to automatically plan and organize and execute collectively to achieve the construction goal. So in today's talk, I will start by briefly reviewing the history and state of the art of construction robotics, because I think this might be helpful for the Asiagraphics community. And then I will share with you some of my recent work on applying automated planning technique to enable more capable construction robotics. And I will start by describing how an intelligent planning algorithm can help us automatically program robots to assemble arbitrary design input. And then I will show you how to expand this to model and program new robotic fabrication processes. And I will end with a resource planning method that can make the design more responsive to the upcycled material inventory. So let's get started. So how to use machines to boost productivity in construction is a topic that has almost 40 years of history. So at first, people aim to replicate the success of automated manufacturing and trying to transport it into the construction domain. And the results was the invention of a variety of specialized construction machines like the polishing robots, brick layering robot, etc. And in order to use those specialized machines, the design of a building is forced to conform to the ability of those machines. So however, this first wave soon died down both because of the collapse of an economic boom, but also because of the inherent rigidity of these building designs and the high expense of those specialized machines. So around 2005, together with the rising popularity of 3D printers and the decreasing price of industrial robots, a second wave of interest in construction robotics started. And however, unlike the last wave that's mostly driven by mechanical engineers, architects and designers start to become the driving force of this wave of development. To realize the potential of industrial robots as a universal machine. They believe that the design should drive the machine, and we should use robots to materialize more complex and diverse spatial forms instead of just a small set of standard forms. So in summary, research before the millennium focuses on using standardization to boost productivity, and the research afterwards, until now, aims at the flexible production of customized designs. However, despite the popular culture show us this is what construction robots should look like, which means huge, gigantic humanoid robots working on site, there are a lot of technical problems to be solved before we can see something like this come true. And I think Professor Kim also illustrated this nicely. Like we have three main type of algorithmic or technical problems we have to tackle for like construction robots. First is sensing, and then control and planning. And for construction robotics in particular, it can be classified into two types. One is on-site robots that can directly move around and work on the construction sites. And the other type is prefabrication robots, where the robot fabricate building components in a controlled factory environment. And then we ship these components to the site, and we use a crane or something like that to manually install them. So my work in recent years focused more on the long-term planning problems, and this has a direct application in prefabrication settings, but also I think it is a very important like a stepping stone towards more robust and capable on-site construction robots. There are mainly two research communities that are pushing planning-related research. The architectural robotics community focuses more on the outcome of the construction, and they push the frontiers of new material, new fabrication processes, and demonstrate the new possibility of design and build with this new technology. And on the other hand, the automated planning in robotics community, I think like some of the graphics community also contribute to this part, work on the more general purpose and effective planning algorithm that can work in many scenarios. From the architectural side, in the past 15 years, we've seen robots can be used to build large-scale complex geometries, and the fabrication process are very diverse, including like spatial assembly, welding, fiber winding, brick layering, etc. And if we classify the literature on construction robots in the past 12 years according to the fabrication processes, we can see that the top four are cutting, layer-based 3D printing. From my definition, I think drawing belongs to something like layer-based 3D printing, where you just have one layer, but have a very long, big one layer, and also stacking and milling. And in the sixth place is spatial assembly, where there's just 1/3 of the articles for cutting in the first place. So my interpretation of this is that the cutting process, we can transplant or trying to borrow a lot of our experience and algorithms, pretty mature algorithms from toolpath planning for CNC machines. But the spatial assembly is something very new, something really enabled by those multi-axis or high degree of freedom robot manipulators. And there are a lot of unsolved technical challenges there. So I conclude that the technical difficulty of programming or planning for the robots is somewhat affecting the research progress of different fabrication processes. To compare it with manual teaching programming method that's widely used in the manufacturing industry, programming of construction robots is much more difficult, in my opinion, because in construction or architecture, we have many, many different CAD models to be assembled, not just one that is repeated many, many times. And we do not really have an accurate physical reference at the first place to do the teaching anyway. So most current architectural robots use CAD software to do some kind of a semi-automated programming. Designers use visual programming platform like Grasshopper and Rhino 3D to program robots point by point based on digital models. But this process takes a lot of time, and the final generated programs are usually not really reliable. So using analogy of a 3D printer that like almost everyone is quite familiar with right now, the process of this programming process is like writing some scripts to generate the G code for each single unique geometry that we're trying to print ourselves by the designer themselves. And on the other hand, in the field of robotics, automated planning algorithms have been studied for many years, and it can be roughly divided into three categories. First, task planning considers symbolic level reasoning issues, like how do you chain together different discrete actions to achieve a goal. And trajectory planning considers how to find a collision-free trajectory that conforms to the kinematic constraints of the robot. And finally, putting these two together is task and motion planning, which is gradually recently emerged a new field in recent years, allowing the symbolic emotion levels to be connected. For example, we can tell the robot at a high level, like make me a cup of coffee, and the task and motion planning engine will automatically reason like which action is reachable and which is not, and then chain together a task sequence as well as the motion plan to achieve this goal. So in the context of construction robots, those developments makes everyone in this field very excited because we see the possibility of automation of this programming process. But on the other hand, these existing work only provide a general algorithmic framework. Their performance on domain-specific problems still needs to be improved. So my work attempts to bring these two fields together. So I strive to simultaneously push for algorithmic development and architectural scale experiments to explore both the new geometric possibilities and more efficient algorithms. So today I will share with you some of my attempts in this direction. The first project investigates how to automatically program a robot to assemble arbitrary bar structures. So we want to generate the equivalent of a slicing algorithm that you would use in FDM printing to allow for more flexible robotic assembly of non-standard elements. But the planning problem here is much harder than just programming a gantry machine like a 3D printer. The spatial assembly requires us to think carefully about the assembly sequence. And for each element, we need to determine where the robot grasps the element and all the joint values of the robot at any single time of the entire process. All of these things together build up an enormous search space. And a valid assembly plan needs to satisfy the structural constraint that prevents us from choosing a very bad sequence like this one that build a cantilevering substructure without building any supporting element below it. This substructure will deform too much under gravity and causing harm to the assembly process. And the collision constraint that ensures the robot does not collide with itself, what it has built, and the environment at any time. As the robot builds more and more, the space gets more cluttered, and the sequence will influence the robot's reachable space. These constraints make these variables intertwined with each other and making finding a feasible plan even more complicated. While motion planning is a well-researched field, it only solves part of the problem. Like motion planner can automatically search for a collision-free trajectory in the robot joint space, connecting a given start and an end configuration. But the designers still need to guess the sequence and grasp and call the motion planner in a trial and error fashion to stitch things together. This obviously takes a lot of time and effort, and when the input design geometry changes, we need to reprogram all over again. So our goal is really to design an algorithm that can do this trial and error more effectively and systematically for us. So I think the best way to formulate this planning problem is using a framework of a state space search. The states represent as the gray blocks here, keep track of the current progress of the assembly. It includes a partially built structure and the robot trajectory for the current step. And an automated search process will go from the empty state where nothing is built and gradually adding elements one by one. And every time it arrives at the new state, it will perform a structural analysis to simulate the deflection of the structure and check if a robot trajectory exists for transporting the bar elements, as well as the collision of the robot trajectory. To check the collision constraint, 4 sampling routines need to be coupled together. So we first sample the grasp, and then sample an approaching trajectory on the bar itself. And then we use a constraint motion planner to check if it can find a collision-free motion to follow the gripper path. I think we're using exactly the same the iterative gradient, randomized gradient descent method as mentioned by Professor Yuan before. And finally, we use the motion planner to compute a collision-free path from the pickup position to this approaching configuration, like using standard planner like RRT star or bidirectional RRT. And the structural constraint requires a finite element analysis of the partially built structure. We use a first-order linear elasticity model, which involves solving a sparse linear system to obtain the structural deformation under self-weight. And we say this state is structurally feasible if the maximum nodal deformation is under a tolerance. It is very important to note that the search will automatically backtrack when the search is not feasible and consider other options until it reaches the goal. So we've already replaced the previously mentioned the tedious manual trial and error approach described before. But there are still challenges preventing this state space search from working for complex structures. We can think of a search of driving in a very thick fog without a map. And this means we can only rely on local information to make decisions without a global view. We need to decide where to go at each crossing, but there are just too many options to choose from. And each time we commit to a new action, checking a new state's feasibility has computational overhead because we need to call the planner, we need to do the finite element analysis. And finally, we want to avoid hitting dead ends too frequently and backtracking too much, which might make our search run for eternity or a very, very long time. The first observation we make in this work is that the standard forward search that just described can easily get stuck because of the collision constraint. And here's an example that the search has too many seemingly innocent options at the beginning, and it keeps making those greedy decisions and only realize, okay, at the very end, an element cannot be reached, and we need to backtrack many, many steps. And to fix this, one key algorithmic insight is that backward search can dramatically reduce those collision-related dead ends. Searching backward is essentially the idea of assembly by disassembly, where we move elements from the complete state to the empty state, just like in a Jenga game. Because we go backward, the planner cannot choose elements that are inside the shape at the beginning because they are pruned by the collision checker. And in doing so, much less backtracking is needed in the long term. In addition to a search direction, a good heuristic is very important to guide our search to save more unnecessary explorations. It's like the road sign that tells you which direction is more promising to get you closer to your goal. Well, an obvious heuristic is to rank the element by the height and always prioritize removing the one that's higher up. This strategy works for many shapes, but failed for a shape like this tower. It would bias the search to remove all the tension ties at the top, and the entire tower will deform as a result. Thus, the search will get stuck in a dead end. And to fix this, we introduce a new heuristic that's bootstrapped by a structurally feasible sequence, which would guide the search to adhere to this example sequence while still allowing flexibility to balance the collision constraint. To obtain the sequence, we first run a forward search without considering the robot, just the structural constraint. And we observe that this heuristic offers a really robust and generic solution to guide the search effectively. Now, combining these two strategies can really give us a fast and scalable planning algorithm. So in contrast to a naive forward search algorithm that cannot terminate in hours, our approach can find a feasible plan for this fairly complex bar structure in 3 minutes and outputs a detailed sequence and trajectory that can be directly loaded on the robot. And we can also plot the maximum nodal deformation along the assembly steps, where each dot on this plot represents a partial structure simulated with the FEA along the sequence, and the y-axis is the maximum nodal deformation of that step. And we can see that the deformation is really controlled below the prescribed tolerance, indicated by the yellow line. And I believe the true power of having this computational planning system is that we can now plan to build all these different shapes without changing any lines of code. And it takes less than 6 minutes of computation for any of these, like a variety of shapes. And another cool thing or advantage of our planning formalism here is that it can be easily extended to other types of robotic fabrication process with a similar pattern of actions. Here we show a spatial extrusion process, which is kind of similar to drawing, but you can imagine like the robot is holding a pen that's drawing in the air, and wherever it traverses, there's a beam or a line of plastic that kind of just solidified right after it traverses. We can now plan for extruding all kinds of complicated topologies and geometry, like this topology optimized beam that achieves efficient load transfer. And you can see this, the last one takes only like under 4 hours to print. And here's another example of a famous and classic topological shape of the Klein bottle. And this planning framework allows us to really experiment with different motion planners. And these motion planners offered by the robotics community really start to become a commodity tools that we can really plug in and play and see which one works the best to achieve our design outcome. And what we gain here is not only an expansion of geometric possibilities, but it also means flexibility in working with different machines. It doesn't matter what robot brand is, how many joints they have, and what customized manufacturer you're using. The planning algorithm is generic and allows plug and play for robot models. And here's one example of using our approach on an ABB robot on a large linear track, a simulated example to extrude a large-scale topological optimized beam that span across 3 meters. So to summarize this part of the work, we designed a search algorithm to automate the planning of robotic assembly. We've shown this framework makes assembly flexible to various design inputs and can be extended to plan for spatial extrusion. Although the current implementation still takes minutes to compute a plan, it can already act like a design check. Ultimately, our goal is really to use this planning framework to make it fast enough to serve as an input in the design process. So by automating robotic assembly, we not only enhance our capability to construct previously impossible shapes, but also gain insights into constructability. And now that we have given a solid planning method for robotic assembly, we want to expand this success to support innovation of other new robotic fabrication processes. Well, robot does not, in those new fabrication processes, the robot does not only just do pick and place of beams, but also change tools. It cuts, it drills, and so on. So as researchers in this field, we all spend a lot of time thinking about how to coordinate those actions and program the motions. But the resulting prototype program usually cannot adapt to new input well enough, and there's a lot of wasted, duplicated programming efforts. And this is really a painful experience that many of us share. And this project really tried to build a generic computational workflow so that designers can model their process on a high level, and the detailed robot plan can automatically be computed. And we take inspirations from computer programming. When you work with a programming language like Python, the composing of executing a program roughly has these 3 phases. The first, you write code that consists of instructions and algorithms that describe the desired behavior of a program, and the compiler takes over and turns it into a low-level representation the machine can understand and execute. And finally, the processor dispatches those instructions to basic computing units, which are specialized to do operations like adding and multiplying numbers. So in our context, our basic computing units are inverse kinematic solver and motion planners. And our goal is to build this compiler for describing the construction tasks and translate them to a format that the motion planner can operate on. And to ground up discussions a little bit more, let me introduce you to a case study from my colleague Victor Liang at the Grandmaster Encoder Research Group at ETH Zurich. And his research proposes a new process where the robot can assemble spatial timber structure with those tightly fit integral joints. Well, humans usually use a big hammer approach to assemble those tightly fit joints. This obviously does not work well with most of our industrial robots today. If you really do that, you push really hard to get the robot to use a hammer, the robot controller, the warranty, and your lab technician probably will scream at you at the same time. So Victor had this idea of designing those remotely controlled clamps that can be mounted on the timber and can generate a large amount of pulling force. Then the robot arm can simultaneously push the timber elements into the joint together with the clamps. So this will overcome this the large amount of friction force required by those integral timber joint. And with this concept, we can already start to organize robot actions and visualize the process here. So the challenge we face here is that there's just so many tasks to be handled and even more motions to be programmed. Even for the seemingly innocent 14-element structure, it would require 671 tasks. And manually organizing these things is certainly not a good idea. So to overcome these challenges, we introduced a flowchart-based compiler and a motion solver. So the compiler allows designer to express their process in this compact, intuitive format. So it's kind of I think it's very conceptually, it's very similar to a finite state machine. So for example, our timber assembly processes flowchart is here. And an important feature here is this conditional statement here. They will automatically curate a variable number of clamp manipulation depending on the considered beam. So starting from the flowchart, the rest of it is automated by our algorithms. So the compiler first translates the flowchart into a long sequence of robot motions. And what is the key here is the compiler breaks down the tasks into smaller movement chunks that correspond to the motion planner's capabilities. For example, placing one single beam takes 69 robot motions, and the color of those little blocks here correspond to their type of motion. Then the motion solver takes this long list of movements and automatically computes robot trajectory for each one of them. And the trick here is to smartly group the motions together. And for each group, it identifies the most constrained motion and propagate outwards. So without getting into too much details here, I just showed that the results shows this strategy greatly reduced the planning time compared to a naive solution that sequentially solves motions one by one. So now it's time to see the fruits coming out of our compiler solver. So this timber structure has 40 elements and involves 2,400 robot motions altogether. And planning the entire construction process takes about 5 hours of computing time. And as you can see, many of the motions involve operating in a tightly cluttered situation, and our solver is crucial for finding those intricate trajectories. And a big advantage of this workflow is, again, this flexibility in adapting to new design geometry. Here I show another design planned and executed using our approach. So in the paper, we also show examples of using this approach to model other previously proposed robot processes, including a multi-robot assembly and a robotic winding process. And what we want to emphasize here is this flexibility in modeling different robot processes, and this can act like a bridge to utilize the power of computational tools already exist from the robotics community. So in summary, we provide a compiler solver approach to fill in this important missing gap between designing a new robotic fabrication process and the automated planning of robot motions. And we've shown its effectiveness in planning for a new timber assembly process, and it provides designer with a flexible means to test and deploy new robotic fabrication possibilities. So finally, I want to talk about a different type of planning to switch from planning actions of robot builders to planning how material resources are used. The main motivation here is to limit the usage of new virgin materials in the built environment and think about how to upcycle or reuse materials that are already available for us in structural waste, either from existing buildings or from the natural world. Things like tree branches that are normally chipped, degraded, and turned into carbon emissions within a year, we could instead try to salvage and use them in generative design process to construct structures with high strengths, where the strengths really come from that amazing internal fiber structures of trees. However, compared to designing in an unconstrained manner, where an infinite material supply, with an infinite material supply, reusing existing material requires designers time, effort, and creativity to devise structural forms with a constrained kit of parts. There's an increasing interest in the idea of designing with reused parts, but we are nevertheless missing a generic computational assignment workflow that can cater irregular inventory geometries and can find an optimal assignment while staying responsive to design change. So this work addresses this need by proposing a matching algorithm that finds the optimal assignments between the target design and material inventory. And the important ingredients here are first using a geometric registration algorithm, classic 1 ICP, to compute pairwise shape differences between the design set and the material inventory. It then uses a specialized matching algorithm, like a Hungarian algorithm, to find the optimal matching, since here we can model this as a linear assignment problem. And with this algorithm, we can start to optimize a parameterized grid shell, not just to maximize the structural efficiency or structural stiffness, but to maximize the use of inventory of tree branches that we have available. You can see here, as we are changing the designs, the matching are changing, and the matching score is also changing. And again, combined with the advances in robotic fabrication, the complexity of building this can be minimized. Here we use a robot arm to machine the tree. Because like we cannot leave the barns, the outer layers of the tree on because of the fireproof requirements. And the assembly process itself cannot be simplified. We're still working with a kit of parts, but our kit of parts is quite unique. It is driven by the natural geometry that we've encountered from the found materials. And this idea can be extended to different types of geometry. For example, reusing timber elements from a disassembled house to design greenhouse domes. And our optimal matching algorithm can give us the best way to assign and cut these salvage materials. And with our tool, designers can start to have a live feedback on material utilization and other objectives while exploring different design options. And it helps them to quantify the trade-off between sampling a design data set with a multi-objective optimization and start to identify this Pareto front between the total floor area and the matching score. So we have also used this technique in our teaching at MIT. Architectural design students use this matching tool to give traditionally undervalued waste materials a new life. For example, start to build a spanning structure with oyster shell pieces, making a light cover with broken beer bottles, and using abolished shared bike frames to start to build trusses. So in summary, in this work, we've shown how a resource assignment algorithm enable us to design with upcycled material resources. And this can start to open up a lot of room for creativity and the use of computation in new ways. So to conclude, today I've really quickly show a few design and construction problems and how the planning of these things can be assisted by computation, by algorithms. And in all of this work, existing computational tools can only solve part of the problem, and we need to invent new tools and a more integrated framework to have them all work together effectively. So just to recap, in the first project, we use an integrated search algorithm to plan for both assembly sequence and robot motions together to program robots to assemble arbitrary design input. And in the second project, we consider a compiler-solver approach to help program new robotic processes. And in the third project, we demonstrated an optimal assignment algorithm that enables us to design with upcycled material resources. And I think this is really a small sample of what automated planning can do. And although we mostly focus on robots, future work would include a more integrated framework that considers human, robots, materials all together, and an idea of a reactive planning to automatically come up with long, short adjustments when construction reality really deviates from the initial plan simulation. And also bring this work really out of the lab to push for applications in real projects. And finally, before I really wrap up, I would also mention that none of those work will be possible without great people. So a huge thank you to all of my mentors, collaborators, lab mates, and so on. But of course, the funding agencies that make this possible. So thank you very much for listening. I would like to open it up for questions now.
Thank you, Yijiang, for your very nice talk. Is there any question posted on the internet? Yeah, because Yijiang is my colleague, so we have discussed many of the questions personally a lot. So if there's a question, I prefer to on the internet, I prefer to ask first. No? Okay. No. Okay. No. No question. So maybe yeah. Let's not instead of ask question. Let's discuss like what do you feel about the future of the robotic constructions? How should we or how this field should grow? What's your vision? It's using robots to build it. It's the ultimate way, or is like what this field could go?
Yeah, that's a very, very hard and challenging questions. So I think, yeah, I think I first got into this field because of just personal interest and this like, oh, using robots, programming them to build things is cool and exciting. And but later, as I get deeper and deeper into my PhD, I start to trying to find motivation in a bigger picture. I think like most of the construction robotics nowadays, it's not, as I showed like in the history, it's not not just to boost productivity, but also it's just really trying to use robots to solve the labor shortage problem. I know like labor shortage might not be a problem in the Asian countries, but as the world is moving into like with more the educated population is increasing, I think the labor shortage will come like in some day, and trying to use robots to at least assist repetitive and tedious tasks in construction. Those tasks that cause injuries and use a lot of time, cause people back pains or something like that, or dangerous. I think this is definitely like a much needed research agenda. In terms of where this is going, I think I've also shown like there's two types of construction robotics. One is offsite and one is onsite. I think like most of the research nowadays is still focusing on the prefabrication setting. Like it's basically where we're still like trying to grow out of the manufacturing setting, like controlled factory. How do we program robots? It's precision engineering. But I think in the future is really trying to push to the onsite, trying to encounter for the how do we sense, how do we make the vision system working, how do we make multiple agents to collaborate. I think is very important and very hard. So I think we're just starting, and this is very exciting research area.
Yeah, I agree too. So thank you again, Yijiang, for your very nice talk.